For decades, quantum computers needed something close to the coldest temperature physically possible in the entire universe just to function. A fraction of a degree above absolute zero, colder than the empty vacuum between stars, maintained inside machines costing millions of dollars. That rule just quietly broke, in at least 4 separate countries, using at least 3 different kinds of physics, all within the same 18-month stretch. A quantum computer built in Australia has been running inside an American national laboratory since late last year, sitting at ordinary room temperature. A Shanghai startup just unveiled one small enough to slide into a standard server rack. Read that again. And now you're being told this means artificial intelligence data centers, the trillion-dollar backbone of the entire modern tech economy, are doomed. That specific claim deserves a much closer look before you believe it. To understand why this moment genuinely matters, and why the doomed part of that claim doesn't survive contact with the actual evidence, you first need to understand exactly what problem room temperature quantum computing actually solves, because it's a genuinely narrow, genuinely important problem. Not the sweeping, world-ending one a dramatic headline might imply. Quantum computers have always faced a brutal, expensive engineering requirement. Qubits, the basic units of quantum information, are extraordinarily fragile, and for most types of quantum hardware, keeping them stable enough to actually compute with has required extreme cold, dilution refrigerators costing millions of dollars, filling entire rooms, consuming enormous amounts of electricity just to protect a handful of qubits from the ordinary thermal noise present in any warm environment. This single requirement has quietly kept quantum computing locked inside a small circle of elite national laboratories and trillion-dollar technology companies, the only institutions on Earth capable of affording that kind of specialized infrastructure. What most people are not seeing is that an entirely different approach has been quietly maturing in parallel this whole time, one that doesn't fight the heat with brute force refrigeration, but instead finds ways to build quantum systems that simply don't need to fear it in the first place. Let's start with the company furthest along this exact path, because their story illustrates precisely how this breakthrough actually works at a physical level. Quantum Brilliance, a company spun out of the Australian National University, builds its qubits using nitrogen vacancy centers, tiny, deliberately engineered defects embedded inside synthetic diamond. Instead of isolating a fragile quantum state and burying it under millions of dollars of cryogenic protection, the company relies on the sheer physical rigidity of a diamond's crystal lattice itself to shield that state from ordinary thermal noise. Andrea Tabacchini, the company's VP of Product and Marketing, explained the underlying physics with striking simplicity. It means we have long enough coherence time, so long enough usability of the qubit, even without the need of cooling down. This isn't a laboratory curiosity confined to a single university bench either. In late 2025, Quantum Brilliance deployed a small cluster of 3 of these room temperature quantum computers directly inside Oak Ridge National Laboratory, one of the United States Department of Energy's flagship research facilities, housed in a rack that, according to the lab's own description, looks remarkably similar to an ordinary data center server rack. The 2 organizations are actively exploring the mechanics of hybrid computing together, working out exactly how quantum and classical processors might eventually share the same physical space. Before this story goes any further, it deserves exactly the same honest, grounding scrutiny this channel applies to every genuinely exciting claim, because Tabacchini himself was refreshingly candid about how far this technology still has to go before it reaches anything resembling commercial maturity. Solving the temperature problem, he explained, is not the same thing as solving quantum computing's other deep, unresolved challenge, the problem of noise and error correction more broadly. Quantum Brilliance is still working through exactly which error correction algorithms would make the system genuinely commercially viable, and Tabacchini was direct about the timeline involved, stating plainly that quantum computers won't hit the market in earnest for, in his own words, a while. Or, this is not chaos. This is exactly the kind of honest, unhurried transparency that separates a genuine scientific breakthrough from an overhyped headline, and it's worth remembering throughout everything that follows in this video. There's an even more pointed piece of skepticism worth including here, precisely because it comes from a company with every commercial incentive to want quantum computing to succeed as quickly as possible. Amazon Web Services has publicly described the entire concept of simply racking and stacking quantum computers directly inside an ordinary data center as, in the company's own blunt characterization, closer to fantasy than near-term reality. Think about the weight of that specific assessment. This isn't a skeptical outside academic. This is one of the largest cloud infrastructure providers on Earth, a company that would stand to profit enormously from quantum computing's rapid commercial maturity, choosing instead to publicly temper expectations rather than inflate them. While Quantum Brilliance has been methodically, patiently building toward commercial viability, an entirely different, considerably more ambitious approach has been unfolding in parallel. one built not on diamond, but on particles of light itself. A Canadian company called Xanadu built something called Aurora, a genuinely remarkable piece of engineering constructed from 4 independent quantum server racks, interconnected through 13 kilometers of fiber optic cable and utilizing 35 separate photonic chips working in coordination. Operating entirely at room temperature, Aurora eliminates the extreme cooling demands plaguing many competing quantum platforms. And according to the system's own architecture, it's designed for something genuinely unusual in this field, near unlimited scaling, potentially expanding to thousands of racks and millions of qubits, an almost unprecedented leap toward what the industry calls utility-scale quantum computing. Xanadu's specific approach sidesteps the qubit fidelity and scaling constraints that have historically trapped quantum computing inside laboratory prototypes, using a modular, networked photonic system that can, in principle, keep growing almost indefinitely by simply adding more racks, rather than hitting some hard physical ceiling the way many other quantum architectures eventually do. Meanwhile, on the other side of the world, an entirely separate ecosystem of room temperature quantum hardware has been developing at a genuinely startling pace. And understanding its timeline reveals just how quickly this specific corner of quantum computing has been maturing. In October of 2025, a company called Zhongke Kuyuan, affiliated with the Chinese Academy of Sciences, delivered a system called Hanyuan-1 to a subsidiary of China Mobile, marking the country's first commercial neutral atom quantum deployment. 100 qubits, operating entirely at room temperature, the whole system fitting inside just 3 standard equipment racks. The system generated real commercial traction, securing genuine customer orders, including an international sale to Pakistan specifically to establish that country's first national quantum computing center. Just 7 months later, in May of 2026, the same research lineage unveiled Hanyuan-2, a dual-core cabinet system operating below 7 kilowatts of power consumption, an almost absurdly modest energy footprint for a working quantum computer, designed specifically for parallel processing configurations. Then, in July of 2026, at the World Artificial Intelligence Conference in Shanghai, an entirely new company entered this exact race, and its specific pitch deserves close attention because it directly addresses the doomed claim sitting inside this video's own title. A startup called Zhongqi Wuliang, a spin-off from the Chinese Academy of Sciences Shanghai Institute of Optics and Fine Mechanics, unveiled a system called Qinghe No 1, described by industry press as the first quantum computer concept designed in a standard server form factor for direct installation in existing data center racks. Think about what that specific engineering choice actually represents. The team packaged the vacuum chamber, the control optics, and the laser delivery systems, all the components a neutral atom quantum computer needs to actually function, into a single standard rack chassis, explicitly so cloud providers could deploy this hardware directly alongside their existing classical servers, rather than requiring an entirely separate, specialized facility. The hardware integration itself was accelerated through a supply chain partner called Xuansheng Technology, which recently commercialized a specialized metasurface chip capable of generating large-scale optical tweezer arrays, a genuine manufacturing breakthrough that simplifies exactly the kind of precise optical alignment neutral atom systems require to actually hold individual atoms in place. Here's a detail worth sitting with for a moment because it reveals just how seriously even the most quantum-skeptical major technology company now takes this exact trend. In early 2026, Google Quantum AI, the same division responsible for the superconducting Willow chip and its headline-grabbing Quantum Echoes algorithm, launched an entirely separate, dedicated neutral atom research program based in Boulder, Colorado, explicitly designed to run alongside the company's existing superconducting efforts. Google cited the neutral atom approach's reconfigurable connectivity and scalability advantages as the specific motivation behind this parallel investment. Think about what it means that Google, a company whose entire public quantum computing identity has been built around cryogenically cooled superconducting circuits, is now deliberately hedging its bets by investing directly in room temperature capable neutral atom technology as well. This isn't one company's isolated bet anymore. It's becoming an industry-wide recognition that room temperature quantum computing represents a genuine, credible parallel path worth pursuing seriously, not a fringe curiosity. It's worth being precise here about a genuinely important nuance, one that separates true room temperature quantum computing from a related but structurally different engineering approach Microsoft has taken. According to detailed reporting from Quartz, Microsoft's current quantum design fits inside a standard server rack and draws about 30 kilowatts of power, but the overwhelming majority of that power goes specifically toward refrigeration. Zulfi Alam, the Microsoft executive leading this effort, described the specific engineering solution in a genuinely memorable way. The cold part itself, he explained, is only about the size of a soda can. Everything else runs at room temperature. Read that carefully, because it's a meaningfully different approach from the diamond-based and neutral atom systems described earlier in this video. Microsoft hasn't eliminated cryogenic cooling entirely. It has miniaturized that cooling down to an almost absurdly small physical footprint. A soda can-sized cold spot sitting inside an otherwise ordinary room temperature server rack. This is a genuinely clever engineering solution, but it's not the same underlying achievement as quantum brilliance's diamond qubits or China's neutral atom systems, which require no dedicated cryogenic cooling of any kind, at any scale, however small. Now, let's turn directly to the second half of this video's own title, because this is exactly where an honest, carefully researched answer diverges sharply from the dramatic framing a viral headline might suggest. Are AI data centers actually doomed? The evidence gathered across every single credible source examined here points toward precisely the opposite conclusion. Not replacement, but convergence. Not doom, but co-location. Consider what's actually happening at IBM right now, not as a future promise, but as an operational reality. IBM has quantum computers already deployed and running real scientific workloads alongside classical supercomputers today. At Riken, Japan's flagship National Research Institute, an IBM quantum system sits physically next to the Fugaku supercomputer, one of the most powerful classical machines on the planet, actively handing off portions of molecular simulations back and forth between the two systems as each calculation proceeds. Jerry Chao, IBM's chief technology officer for quantum-centric supercomputing, described exactly where this trend is heading. We're moving into a data center model, he explained, where we're actively looking at co-located CPU and GPUs with quantum processors. Read that sentence again and notice precisely what it does and doesn't say. Co-located, not replaced, not rendered obsolete. Sitting in the same room, working on the same problems, each system contributing the specific piece of computation it happens to be genuinely good at. This exact pattern, quantum hardware moving in alongside classical infrastructure rather than displacing it, shows up consistently across every single credible source examined for this video, and it directly contradicts the doom-laden framing this video's own title implies. A detailed piece of industry journalism covering exactly this intersection captured the shift with genuine precision. For years, the reporting explains, AI data centers and quantum computing have been covered as separate stories with separate problems. One is about gigawatts, grid strain, and utility fights over who pays for the build-out. The other is about lab physics, cryogenic cooling, and breakthroughs that are always a decade away. That separation has started to collapse. Notice the specific word chosen there. Collapse, in the sense of two separate categories merging into one, not in the sense of one category destroying the other. This is precisely the distinction this video's title gets wrong, and it's worth correcting clearly and directly, because getting this specific nuance right actually makes the true story considerably more interesting than the false one. Here's the single most important sentence buried inside all of this reporting, one worth repeating with exactly the same directness the original source used. One thing quantum is not going to do is make the data center energy crisis go away. Read that again and sit with exactly what it means for the entire premise sitting inside this video's own title. The gigawatt scale electricity demand currently driving AI data center construction across the entire world, the same demand forcing utility companies into desperate negotiations, the same demand pushing tech giants toward nuclear power contracts. None of that gets solved simply because quantum processors are learning to fit inside the same buildings, at room temperature, alongside classical GPUs. Room temperature quantum computing arriving inside the data center isn't a rescue mission for the energy crisis already unfolding there, and it certainly isn't a death sentence for the classical infrastructure driving that crisis in the first place. It's something else entirely, a new specialized capability being carefully layered on top of an existing infrastructure problem this specific technology was never actually designed to fix. Think carefully about why this distinction matters so much once you actually understand the practical division of labor emerging between these two fundamentally different kinds of computing hardware. Classical GPUs, the exact chips currently, filling AI data centers around the world, remain extraordinarily good at exactly the kind of general-purpose tasks that make up the overwhelming majority of everyday artificial intelligence work, training massive language models, running inference at scale, processing the ordinary business, computing that has nothing to do with quantum mechanics at all. Quantum processors, room temperature or otherwise, remain fundamentally specialized instruments genuinely powerful for a narrow set of problems involving optimization, certain categories of chemistry and material simulation, and highly specific mathematical structures that happen to align naturally with quantum physics. While remaining, it changes where and how cheaply the specialized quantum tool can physically be deployed in the first place, moving it out of an isolated laboratory environment requiring millions of dollars of supporting infrastructure, and into something that could eventually sit inside an ordinary server rack in an ordinary building, right alongside the classical hardware it will most likely continue working with, rather than replacing, for many years still to come. There's a genuinely fascinating strategic thread running underneath all of this worth pulling on before this story reaches its conclusion, because it reveals just how dramatically industry attitudes toward quantum computing have shifted within an astonishingly short window of time. At the start of 2025, NVIDIA CEO Jensen Huang began the year by publicly downplaying quantum computing's near-term significance, emphasizing its immaturity compared to classical computing, and openly casting doubt on whether the technology was ready for any kind of practical application at all. That specific comment, delivered at a major industry event, briefly wiped out billions of dollars in quantum computing stock value within a single trading day. And yet, by October of 2025, NVIDIA had launched NVQLink, a real-time interconnect specifically designed to connect quantum processors directly to NVIDIA's own classical GPUs. By April of 2026, the company had released Ising, an entire family of AI models, purpose-built specifically to help quantum hardware companies manage the exact kind of calibration and error correction problems standing between today's laboratory demonstrations and tomorrow's genuinely useful machines. Think about what that specific reversal actually reveals. The single most quantum skeptical major executive in the entire technology industry, within roughly 15 months, went from openly dismissing quantum computing's near-term relevance to building an entire layer of infrastructure specifically designed to help that same technology succeed. That's not the behavior of a company bracing for its own obsolescence. That's the behavior of a company that has concluded, after careful, deliberate analysis, that quantum computing represents a genuine opportunity to extend its own infrastructure dominance into an adjacent complementary market, rather than a genuine existential threat requiring urgent defensive action. So, where does the honest, carefully researched answer to this video's own title actually land? Room temperature quantum computers are, without question, genuinely here, verified across multiple independent companies, multiple countries, and multiple fundamentally different underlying physical approaches, diamond nitrogen vacancy. Centers in Australia and Germany, photonic systems in Canada, neutral atom architectures across an entire rapidly maturing Chinese commercial ecosystem, and even Google's own quiet hedge into neutral atom research in Colorado. This represents a genuine, historically significant engineering achievement, one that finally, credibly threatens to dismantle the single most expensive, most deployment-limiting barrier that has kept quantum computing locked inside elite laboratories for the better part of 2 decades. But AI data centers are not doomed, and every single credible source examined for this video points toward precisely the opposite outcome: deliberate, deepening integration rather than displacement. IBM's quantum systems already running real workloads alongside classical supercomputers at Riken today. Microsoft's soda can-sized cold spots sitting inside otherwise ordinary server racks, and NVIDIA's own dramatic strategic reversal from public quantum skepticism to active infrastructure investment within a matter of months. What's actually unfolding here is something considerably more interesting, and honestly, considerably more useful, than a simple story of one technology conquering another. It's the slow, deliberate construction of a genuinely hybrid computing future, where classical and quantum processors sit in the same racks, in the same buildings, each one handling exactly the specific category of problem. It happens to be naturally best suited for working together rather than fighting for the exact same job. If you want to understand exactly what happens once these room temperature quantum systems finally combine with the kind of large-scale error correction breakthroughs covered extensively across previous videos on this channel, the moment when the temperature problem and the noise problem both finally get solved on the same piece of hardware at genuine commercial scale, that's precisely the story we'll be tracking closely as it continues to unfold. So make sure you're subscribed before that convergence finally arrives. Before you go, I want to know what you honestly think about everything you've just heard. Does the genuine, rapidly accelerating pace of room temperature quantum breakthroughs, spanning Australia, Canada, China, and now even Google's own quiet hedge in Colorado, convince you this technology is finally ready to move beyond the laboratory? Or does the continued, deliberate emphasis on co-location rather than replacement tell you the honest future here is genuinely hybrid rather than the dramatic, one-sided takeover a headline like this one might have led you to expect? Leave your honest answer down in the comments below, and as always, I read every single one.